Hello everyone. So welcome to this new course on thermodynamics and kinetics which is offered through NPTEL, and this course is designed at an advanced level compared with the earlier course which I offered in the last semester, and that was at an introductory level course on the same subject. So we'll first give you an overview of the earlier course in which we covered the general or the introductory level various aspects of thermodynamics and chemical kinetics. So to begin with, we will first discuss on the properties of gases. So let us start with that topic, the properties of gases. Now, when I tell the properties of gases, it means actually any. We have to first define the phases of matter. As you know that in classical thermodynamics, we always talk about matter as a macroscopic system, meaning we do not give any particular microscopic detail how the matter is composed of. Like you know already that any matter is composed of molecules, and molecules are composed of atoms. So this kind of detail is not necessary to describe classical thermodynamics. Similarly, the nature of energy is also not necessary, in the sense that for example, the form of light, you know that light is an electromagnetic wave. You can also explain it in terms of energy quanta, which are known as photons. So those descriptions are not necessary. We just use this macroscopic or general description of matter and energy, and will establish relation how matter and energy are basically interact with each other, and which lead to some physico-chemical transformations. So matter continuously exchanges energy with the surrounding system, and then we actually see the effect of the system, of the process which the system is undergoing on the surrounding, and that is how we make actually interesting experimental arrangement to formulate some laws in classical thermodynamics. Now to begin with, as you know that matter can exist in three major forms: solid, liquid and gas. And we will start with the simplest form of matter, which is the gaseous form. Now whenever we talk about matter in a macroscopic sense, we have to first define what is the state of the system. Now as we know that for a state of the system are defined by something which are known as state parameters, and the most common state parameters are pressure, volume, temperature, and of course sometimes we also write the number of moles of the gas molecule or something like that. So we have to establish a relationship between this pressure, volume and temperature, so that we have a functional form. Say I ask you how the pressure is actually changing if I change temperature or volume or say number of moles. So that functional relationship which connects all these macroscopic state parameters is called an equation of state. So that equation will describe or completely describe the state of the macroscopic system. So equation of state is nothing but, suppose we are writing the equation as with respect to pressure. So we write that pressure is a function of volume, temperature and the number of moles. We have to find out what is the equation of state for a particular gas. Now again, so we make some approximations, and those approximations for the gas molecules will lead to something which is known as an ideal gas equation. Already you know all these concepts, but I am just restating all these basic concepts so that we are all on the same page. So as you know that the ideal gas equation means actually the molecules in the gas behaves ideally, in the sense that there is no intermolecular force, and also this there is no explicit volume of the molecules, in the sense that they are just point masses. So if we make that approximation, we see that this equation of state has a particular form, and already you know that particular form is something like PV is equal to nRT, which is the ideal gas equation, and which actually people observed on experimenting on gases which are real gases, but at a very low pressure regime and a high temperature regime. As you know that initially this actually equation, ideal gas equation, came from something like the Waals law, which actually states that the pressure is inversely proportional to the volume, as well as the Charles law, which actually says that V will vary as the absolute temperature. And by combining Boyle's law and Charles' law along with the Avogadro's concept, we got the ideal gas equation, which is PV equal to nRT. Now, if we want to plot how the functional form of P looks like following this equation, PV equal to nRT, we will get basically two variables. Let's say that n is fixed. So, my variables are here temperature and volume, and the function that we are going to plot is the pressure. So, it will be a three-dimensional plot because there is one function which is the pressure. Suppose we are plotting the pressure along this axis, and then I am plotting the volume along this axis and temperature, let's say, along this axis. Now, we will get think about it like if I have a just two function that y is equal to function of x, where x is the variable and y is the dependent parameter. So, then it will be a line because it's if it is not a multivalued function, it will be just like a line. Now, if we have actually z is a function of x and y, so we will have a surface. So, we will have a surface plot in this case also, and let us try to draw how this surface plot will look like. On this axis I am plotting T. I can equivalently say that I can plot the temperature axis along here, and then let us draw the surface, and what we can first draw is this isosurface. Let me erase some part. So, this axis, remember, is the temperature axis, and this axis was the volume axis, and the vertical axis is the pressure axis, and this is the pressure, how basically the pressure changes. That is basically a kind of three-dimensional plot which we have tried to draw here, and on this 3D plot we see that there is a surface. So, this surface tells me that this is basically equation of this surface P equal to nRT by V. Now, any point on this surface actually is represented by this equation PV equal to nRT. Now, if I actually fix temperature, which means I have to take a slice along a particular temperature. Let's say I am talking about this temperature, which has a particular value, and if I actually take a slice, then I will see that the curve will look like something like this, how the pressure is varying with volume. So, if I plot it separately, it will be something like this, which is nothing but the Boyle's law. Similarly, I can actually recover the Charles law, at a particular fixed pressure, how it basically the volume varies with temperature, and this is known as isobar, and this is known as isotherm because actually Boyle's law you kept the temperature constant, and similarly you can also do isochord where the volume is kept constant. So, this surface actually is represents again the equation of state, and the Boyle's law and the Charles law, or the isotherm, isobar, as well as the isochords, can be actually recovered from this generalized surface. Now, moving on, next we talk about how the pressure varies, or how we can actually define pressure for not a single component system but a multi-component system, in the sense that I have few gases, let's say, together, and then I call it as a mixture instead of a multi-component system. So next we talk about what is known as the pressure, what are the expression for the pressure for a mixture. So in that case, you know that we can always define some quantity which is known as the partial pressure, and which is related to the total pressure, as it is the mole fraction of that ith gas times the total pressure. Now the partial pressure is defined, suppose I have a container and I have two gases A and B, and now A has some pressure and B also exerts some pressure, and so that the total pressure will be the addition of these two pressures, because it's basically related to the total force the molecules generate by bombarding on the wall, so that has to be additive. And pressure is just force per unit area, so pressure is also additive. Now you can think that the partial pressure will be something like that if the one particular gas, let's say the A gas, if it occupied the entire volume, in the absence of the other gas which is B, that will be the partial pressure of A. And the moment we insert the second gas B, similarly the B will also have a partial pressure if A is absent. So together, when they are present in a mixture, the total pressure will be the addition, and that's how we get the relationship from partial pressure with the total pressure. Now this pressure has a molecular origin, although we do not we said that it is not necessary for us to go back to a molecular picture, but when we discuss the reaction dynamics in gas phase, there actually we talk about how the molecules are coming together, they are colliding, and what is the energy criteria, that there is a threshold energy that you need to cross for the reaction to happen, and those things when you consider, then you have to actually invoke a very much molecular level picture. And we'll give a very simple description here, and here the atoms and molecules again are considered to behave ideally, in the sense again they do not have any intermolecular interaction, there is no interaction potential between two atoms or two molecules. And when I say two atoms or two molecules, I am saying I mean that the gas is either composed of atoms or molecules. For example, if I talk about helium gas, so helium is monatomic, so it's between atoms only. And when I talk about say methane gas, it's basically the interaction between methane molecules. But if the gases behave ideally, so the point here is that the individual particles, which are either atoms or molecules, they do not interact with each other, and secondly they are regarded as a point mass. And since they have still a mass, so the pressure you can express as a rate of change of momentum divided by area, because according to Newton's third law, the rate of change of momentum is identical to force. Now how do you calculate the rate of change of momentum? You can actually calculate how many molecules are striking the wall of the container, and then if you actually assume that there is some average velocity with which the molecules are striking this wall, so then actually you can derive a formula which you have seen definitely in your introductory level course on kinetic theory of gases. And there finally we get an expression for pressure as P is 1 over V, and then there will be a 1/3 factor. So this factor actually comes from the isotropic nature of the molecular speed, times n is basically the number of moles, times capital M, which is the molar mass, and then I have Vrms square. Now what is Vrms? Vrms is basically the root mean square velocity. So it's the square velocity, and then I take the mean squared velocity, which is basically taking the average of the square velocities, and then I take the square root of that. So that's how the name comes, it's root mean square velocity. So we get an expression for pressure, and this expression now we can actually further modify this expression, because we know that the ideal gas equation, that P times V is equal to nRT, and if we plug in all the things, then we get an expression for the RMS velocity or the root mean square velocity, and that will be 3 RT by m. Sometimes we, instead of r, we actually express it in terms of the Boltzmann constant. Remember that m is the molar mass, which is nothing but mass of an individual molecule times Avogadro number, because 1 mole contains Avogadro number of atoms or molecules. So we can actually write it in that way. Similarly, r is nothing but the Boltzmann constant, which we write as k suffix b, that the b denotes the Boltzmann constant, and times it is the Avogadro number. So if we plug in these two conditions, we get in terms of the Boltzmann condition, Boltzmann constant, it is 3 kBt by small m, where small m is the mass of the molecule or individual atoms. So thus we get expression for the RMS. This is for of course this is for an ideal gas or a gas that obeys the ideal gas law, which is PV equal to nRT. Now this much information from the kinetic theory of gases is sufficient, and then what we discuss is that in a collection of molecules, because a gas means it's a macroscopic system and there are many molecules, and all the molecules will not actually have the same velocity. There will be a distribution of molecular velocities and distribution of molecular speed, and by speed we mean that only the magnitude of the velocity independent of any direction. Now the velocity distribution according to the Maxwell-Boltzmann distribution law assumed, it's not assumed, it is also, there are many arguments why the velocity distribution along a particular direction. If I just write it as a f of Vx, where f is nothing but a probability distribution of the fraction of molecules which have, say, velocity from in the range Vx to Vx plus dVx. If I define it in that way, so that will be something like some constant times e to the power minus b Vx square, and that's a Gaussian function. So in the sense that if I plot the velocity Vx along this direction, so the distribution will look like a Gaussian distribution. And remember that the velocity is when the velocity is 0, that actually picks up, in the sense that the velocity has both positive and negative direction. So but from that actually we want to know how the speed distribution looks like, which means actually we will just talk about the magnitude of V independent of the direction and some probability. So this probability now actually tells you what is the fraction of molecules having speed in the range V to V plus dx, V plus dV, where V is nothing but Vx square plus Vy square plus Vj square, and taking the square root of that. And if I want to derive that, so then there are a few steps which we discussed in earlier course, and finally you will get an Maxwell-Boltzmann distribution law in this form. So it's 4 pi and then m by 2 pi kBt raised to the power 3 by 2. Instead of m by kb, we could have written as capital M by r also, into e to the power minus m v square by twice kBt into v square dv, where v again is a molecular or atomic speed, not the velocities. So this distribution law is known as Maxwell-Boltzmann distribution law, which is already known to you. Maxwell-Boltzmann distribution law. Now think about it, this is a probability distribution, as I said, because Fv dV is basically the fraction of molecules or the probability of the molecules having speed in the range v to v plus dv. So, you can calculate any other quantity from this. For example, if I want to know what will be the value of the average velocity. So, then all I have to do is that I have to take the velocity, multiply with the probability distribution and integrate over all possible distribution of speed. Now, in this case the speed distribution will go from 0 to infinity, it cannot go to negative because it is a speed distribution, and that you can easily work out using gamma function, and you will figure out that the value will be 8 kBt by pi m square root of that. So, that is the average velocity, and similarly we can talk about a velocity which is the most probable velocity, but before that let me just plot how this function looks like. So, this function has basically two parts. As you can see, there is a exponential part e to the power minus bv square, and there is a v square part. So, the exponential part will actually be something like decaying like this, and the v square part will actually dominate. V square part actually will be something like this. So, let me redraw it once again. So, what I am saying here, this function is actually composed of two different functions, or multiplication of two different functions. One is e to the power minus v square, some constant into v square, that actually goes like this, and then there is it is just a v square term which is actually a quadratic function which will be something like this. So, if I take a multiplication of these two, this actually looks like this function. So, it actually goes through a maximum, as you can see, and if we want to calculate what is this speed which is most probable, and then all we have to do is that you have to take that function and take the derivative of that function and set it to be 0 to find the maxima and minima, and that will give you the value of the most probable distribution, and that you will get as v most probable is twice kBt by m raised to the power half, and already we talked about Vrms in the previous section. I am writing it once again, and that from ideal gas equation we got it as 3 RT by m, or let me actually use the similar notation kBt and small m. So, we can write it as 3 kBt by m square root of that. So, we have actually definition of three different velocities. One is the root mean square velocity, that is directly connected to the pressure of the system, and the second one is basically the average velocity, which is 8 kBt by pi m, and then the third one is the most probable speed, which is basically the speed where actually the probability distribution is maximum, or which is the most probable value of this speed distribution, or basically which is at the speed at which the probability distribution maximizes. Now, having all these things in mind, next thing what we try to calculate is basically what is the number of collision in the gas molecules, because that will be very important in calculating the reaction rates, because any reaction in a gas phase or liquid phase, any condensed phase is actually promoted initially by collision. And for that actually you try to calculate that the number of collision that one particular gas molecule makes with many other gas molecules, and then you think that okay fine, let us consider a cylinder of length say v, because this is the time, this is basically the length which this particular molecule will traverse per unit time, because that is identical to its speed. And then you talk about that whatever molecules are suppose this molecule is going inside and it is its trajectory, and other molecules for which the center is actually lying within this cylinder will collide, because it is very easy to understand that if a molecule has a diameter like this and it is moving in a straight trajectory, and if a molecule actually lies out, it will not collide. The collisions will happen if the center of the molecule lie in such a way that they just touch or they are inside. So all these molecules actually will collide with this particular molecule, but this molecule won't collide. So in a sense, what we are saying here, we are talking about some cross-sectional area which is important, and which basically is the cross-sectional area of the cylinder, and all the molecules for which the center of the molecules are within this cylinder will actually collide with this particular molecule, and that we can actually calculate very easily. And you can actually just calculate the volume of the cylinder. You take the number density, multiply with the volume, you get the total number of molecules, and from that you can actually calculate the collision frequency in terms of this cross section. If I call this cross section as sigma, so then we get an expression for the collision frequency, and that collision frequency expression will be something like, if I call it as a Z, and Z will be nothing but sigma times V. It's actually not V, it will be actually V relative, and because it's a relative velocity, because we said that one molecule is moving, all other molecules are static. This is perfectly fine, because we are actually considering everything in a relative velocity frame, not in the absolute frame or the laboratory frame, and then multiplied by the volume. And then we can actually, not volume, it will be the number density, which we denote as say capital N, and then that actually we can rewrite as sigma into V relative into P by kBT, if P is the pressure. So this is the expression for collision frequency, that is the number of collisions a particular gas molecule makes per unit time per unit volume. And now the interesting thing is, what is interesting quantity to look at is the mean free path, meaning actually it is the distance a particular gas molecule travels between two successive collisions, and that you can again very easily understand how to calculate. So per unit time actually it travels the V relative distance, and then we also know that per unit time it is making so many collisions, Z collisions. So by logic, actually this mean free path, which is basically the distance traversed between collisions, will be basically the total distance traversed per unit time divided by the number of collisions per unit time, and which will be nothing but, if I plug in all the relations, all the expression, so it will be nothing but kBT by sigma into P. Now one thing we have written here as V relative, but in reality it will be the average of the V relative. Now the question is, what is average of V relative? And as you can see that it is basically the average speed, but it is the relative average speed. Now you can think that what is the relative speed between two molecules. Suppose one molecule is static and the second molecule is moving, so it can have actually a head-on collision, that is one probability. It can also have something which is known as a grazing collision, meaning the molecule just touches the other one, the surfaces just touch. And it can also have a collision with respect to the other molecule in a 90 degree. So considering all these possibilities, you can think that we can have a 0 degree collision, we have a 180 degree collision, something like that. But 180 degree collisions we are not considering because it's a relative velocity. So it can have a 0 degree collision, it can have a 90 degree collision, and if you take the average of this, so you can think that one molecule is moving like this, the other molecule is basically moving like this at an angle which is 45 degree. So if you take that, so you have to take the projection of the velocities, and the V relative will be nothing but just by from vector relation, square root of 2 of the average velocity. So if you plug in all this relation, you will find that just like we had the expression for average velocity, that V average was 8 kbt by pi m. So you can easily figure out the relative velocity will be 8 kbt by pi mu, where mu is the reduced mass of the two particle system, and it is defined as if I am considering actually the relative velocity between two molecules which are A and B. So then mu is nothing but MA MB by MA plus MB, which is the reduced mass of the two particle system. So up to this point we actually we have discussed what are the basic concepts of the kinetic theory of gases, what are the properties of gases, taking into account of the fact these gases are behaving ideally, or basically we are following ideal gas law. So the obvious question is what happens if the gases do not behave ideally, or there is a deviation from ideal behavior, and which is what we observe in reality, because gases must be real gases, and all real gases behave ideally under certain condition, which is like at very low pressure and a very high temperature. So what is the equation for actual reality, because the PV equal to nRT does not hold other than at a very low pressure and very high temperature. So in order to do that, we have to devise or find some model that can successfully explain the behavior of gases at other temperature, at say normal temperature and pressure. So then we actually talk about real gases. But again, all gases are actually real gases. Real gases show ideal behavior in the limiting case. So we will now talk about the properties of those, properties of real gases, or in some sense the properties of gases actually in any condition, not only at a limiting condition where only the ideal behavior is shown. So let us now start our discussion on the properties of gases, or properties of real gases. So the first thing we discuss when we discuss the properties of real gases is what are the deviations from the ideal behavior from real gases, and then we talk about two important experimental observation, and one is known as Amagat's curve, or which are actually based on the experiments by Amagat. And what Amagat plotted is basically a quantity which is known as the compressibility factor, and which is defined as Z, but do not get confused with the this Z and the collision frequency Z. So maybe we can actually write it as Z comp, and that is defined as the molar volume of a gas and its ratio to the ideal molar volume, or the molar volume of an ideal gas, which means if the gas behaves ideally, the compressibility factor will be 1. If the gas's volume is actually more than the ideal volume at a particular pressure and temperature, so which means actually now the gas occupies more volume than the ideal volume, or the gas is actually less compressible. Similarly, you can think that if the actual volume, or you can actually put a suffix like the real volume, is less than the ideal volume, which means the compressibility factor is less than 1, then the gas is more compressible. So all we want to do is get an expression for the compressibility factor, and we know that V bar, again the bar notation is for 1 mole, and V bar ideal is nothing but RT by P following ideal gas equation. So this is nothing but P into V real divided by RT, and this is the expression for compressibility factor. And when Amagat plotted this compressibility factor Z versus pressure, and remember that for ideal gas it will just be some curve which is around at 1, because the compressibility factor is always 1 for ideal gas. And for some gases, he observed that this is always increasing, in the sense that the gases are less compressible, and the example is hydrogen at again room temperature, and which means actually it is a temperature dependent. We will come back to it. And then for other gases, let us say for methane, he observed that there is an initial dip and then there is a rise. And when he repeated the same experiment for different gases at different temperature, he observed an interesting observation. Again, the Z equal to 1 line corresponds to the ideal gas behavior, and he found that for a particular gas, if we just keep on changing the temperature, we will see curves like this. So, for a particular intermediate temperature, he found that this curve actually more or less lies on the ideal gas, or the gas actually behaves more or less ideally, because as you can see that the slope is actually flat with respect to the x axis where we are plotting the pressure, but this happens only in the low pressure regime. So, that is something important which will come back. And then the other experiment, so this is for the same gas at different temperature. So, this was discussed in the earlier earlier course, or you can also get it from any standard textbook which have been recommended to you. And then the second thing is the Andrews experiment. So, these are also experimental observation on liquefaction of gases. Liquefaction of gases. Now, liquefaction means actually if I increase the pressure and decrease the temperature, any gas actually condenses to form liquid, and the existence of liquid phase, or basically this existence of this phase transition, clearly tells that there must be some attractive force between these gas molecules which actually forces them to form liquid, because we know that due to the intermolecular interaction, the attractive potential, the molecules are forming liquid. So, which means actually this assumption in the kinetic theory of gases that there is no intermolecular interaction is not correct. And let us try to plot the Andrews experiment, what he actually observed. So, Andrews was trying to plot the pressure volume plots, which are nothing but isotherms at different temperatures, and he found that a typical curve actually looks like this. So, this region is basically the vapor region or the gas region. So, it happens at a very low pressure regime. As you can see, it is at the bottom of this pressure axis, and the very low value of the pressure, and at a very high value of the pressure, this is basically the liquid region. So, the gas is already liquefied, and in between he observed a flat region where actually even if we are changing the volume at a particular pressure and temperature. So, this is for a particular temperature, let us say T, let us say T1, and for that particular temperature and the pressure, basically the condensation happens. So, a phase transition is happening at a particular pressure and temperature, and then the volume actually is shrinking, and this volume when it shrinks, the pressure or temperature is kept fixed. And similarly, if you what he did is that he repeated these experiments for higher temperatures, and what he found that this particular region actually shrinks, this the region over which the phase transition happens, and ultimately it reduces to a very particular point above which. So, these are at various temperatures, let us say T2, T3, this is T4, this is T5, where we have the T5 is the highest temperature, and then he basically showed that we have a region comprising something like the liquid vapor equilibrium, and that region basically vanishes above a particular temperature, and that temperature he called as a critical temperature. So above critical temperature, always the substance actually behaves as if it is a gaseous substance. So that's why we made a comment that at a very high temperature, the ideal gas law is obeyed. Although we are telling that at this temperature, which is T5 in this case, which is higher than the critical temperature, we are calling it as it behaves as an ideal gas, but the substance is not actually gaseous anymore. It is called a new state of the system, which is known as the supercritical phase or new phase of the system. Now, in order to explain all this behavior, which is the Amagat's curve, which actually talks about the compressibility factor, and the Andrews curve, which talks about the liquefaction of gases, then many theoretical models came up, and one of the very simple but yet very elegant model is that one which is put forward by van der Waals. And the van der Waals equation of state is something like this: P plus n square A by V square where A is a constant into V minus NB, and B is also a constant, is equal to N at T. Or we could write it in the molar volume notation, in the sense that for 1 mole it will be something like P plus A by V bar square into V bar minus B is equal to RT. So this is the van der Waals equation of state, because again this actually explains the state of the system. And if we want to plot this equation, how the pressure, volume, how the isotherms look like, we will see that this actually has a typical behavior like this. And if you remember that Andrews curve, this region was kind of flat when the liquefaction was happening, but van der Waals equation of state actually shows that there is an interesting dip and rise behavior as we increase the volume or lower the pressure. Now, it actually successfully explains the gaseous region as the liquid region, as well as this change in the phase. And if we actually keep on increasing the temperature, it also shows that there is an existence of a critical point at some particular temperature. Again, we are using the similar type of notation. And then from that equation, you can actually solve for the critical temperature, what are the values of the critical temperature. You can actually analytically get an equation from the van der Waals equation of state. And how do you do it? You see here that when we have a particular pressure, let's say this pressure, I have actually 3 volumes, as you can see here. This is just coming from the nature of the curve, and if you look at it carefully, it is actually P plus A by V square into V minus V is equal to RT, and which means actually it's a cubic equation in V cube. So it's a cubic equation for V bar. So for any cubic equation, you will have 3 roots, and these are the basically 3 roots which I can write it as V1, V2 and V3. So when you solve this equation, you should get 3 roots, but at the critical point, all these 3 roots actually merge together to a single point. So all the roots become degenerate, and that way you can actually easily solve this equation and basically talk about the maxima and the minima, or actually you can say that all this you can actually factorize it into different terms like we actually solve a cubic equation, and that way you can actually figure out what is the value of this critical temperature. And this value of this critical temperature is 8A by 27 Br. Similarly, if you call that at that critical temperature, if I call the corresponding volume as critical volume and the corresponding pressure as critical pressure, you can also figure those out. So the corresponding volume will be 3B and corresponding pressure will be A by 27 B square. So using the van der Waals equation of state, one can actually get an expression for the critical temperature, as well as critical volume and critical pressure, which is great because this is a model which shows that look, I can analytically find an expression for and also explain the existence of this critical state and also explain the liquefaction of gases. Similarly, one can also explain the compressibility factor. I am coming to that. But before that, a little comment on this constant A and B. So, the A actually comes from the intermolecular interactions, which you already know when you studied the van der Waals equation of state, and that basically tells that the actual pressure will be always less than the real ideal pressure, because when the gas molecule is going to strike the wall, it actually experiences a pull of the other molecules which are behind it, which is at the bulk, and so its speed is actually slowed down. And secondly, the volume occupied by the gas is actually, there will be some excluded volume, in the sense that every gas molecule actually possesses some finite volume. So, these two things actually leads to conceptual development of this equation. But again, A and B here are empirical parameters, which means actually you have to figure it out or you have to experimentally determine these parameters for various gases, because the attraction force, intermolecular attraction force, or the molecular volume for methane and for hydrogen will be very different. So, A and B are actually dependent on the gas molecules. Now, the question is this a limitation of van der Waals equation? Which is not true, because actually you can always define some quantity which are known as the reduced parameters or reduced state variables, in the sense that I can always write suppose I have a pressure, and I can always take a ratio of the pressure to the critical pressure. We can call it as a pi. Similarly, some textbook actually write it as PR or P reduced. Similarly, the volume we can actually define as the volume by the reduced volume, and some reduced temperature we can also define as the temperature divided by the critical temperature. And if we actually plug in this relationship into the van der Waals equation after some algebra manipulation, we can show that everything actually reduces to a very nice equation, which is pi is equal to 8 tau divided by 3 phi minus 1 minus 3 by phi square. So, this equation is obtained after you start from the van der Waals equation of state, which is P plus n square A by V square and all this thing, and then you use the values of A, B and R in terms of PC, VC and TC, and then you actually write the P by PC as the reduced pressure, and this way. And now you see that we actually get a very fantastic equation, which is basically the van der Waals equation in its reduced form, in the sense that now this equation does not contain any A or B, which means now I have actually removed the dependence of the van der Waals equation of state on a particular gas, because it is now independent of A and B, and now I can actually plot it. And then if I plot pi versus phi, that equation will be same for all the gases, because it's all already the critical pressures has been divided. So, all this explicit dependence on the constants A and B, which are actually some kind of molecular parameters, can be removed if I express the equation of state in this particular form. Now, the next thing which we discuss in van der Waals equation of state is that you can actually calculate what is the compressibility factor, which actually Andrews described. And remember that the compressibility factor is the idea is that at what temperature this compressibility factor is more or less equal to, behaves like an ideal gas. And if you see this condition that which I have circled here, that at some intermediate temperature any gas actually behaves and ideally in the low pressure regime, of course, because at a very high pressure regime, as you can see this part, it is again deviating. So, what you can do actually using the van der Waals equation, you can actually evaluate this quantity, how this what is the slope of this Z or the compressibility factor curve with respect to pressure, and that keeping the temperature constant, that actually you can set to be 0, but you have to remember that this is in the limit of P tends to 0. Now, if you do it, then you will see that there is a temperature which is known as the boil temperature, and this temperature, I mean it will be basically at that temperature this will be 0, and then you can see that the expression for the boil temperature is very simple, and it actually depends on the ratio of A and B, which are those molecular parameters. So, this ratio will basically tell you that what is the boil temperature for a particular gas, which means actually at that temperature, at a very low pressure regime, the gas will behave ideally, and above the boil temperature you will have or below the boil temperature the gas will have deviations, as we have shown here. So, so those and at a particular if the temperature is equal to the boil temperature, then the gas will behave ideally. So, thus actually the van der Waals gas also van der Waals gas equation or van der Waals equation of state also explains the nature of the compressibility factor for a particular gas. For a different gas, the reason that at a particular temperature they are very different is that for one particular gas, maybe actually the particular temperature is higher than its boil temperature, and for the other gas actually it is lower than its boil temperature. So, they will behave very differently, and thus the van der Waals gas equation satisfactorily explains the existence of critical state as well as the compressibility factor. However, it does not fully actually explain the nature of the curve, because as you can see we have it's a cubic equation and we have basically 3 roots as we have shown here, V1, V2 and V3. So, but what we saw actually at a particular pressure and temperature, we have when the phase transition happens, the volume actually changes, volume actually strains. So, it cannot correctly explain the equation of state or correctly explain the real gas behavior. So, for that there are many other equation of states also, for example, Bartholomew equation of state, Dieterisi equation of state. There are many other equation of states have been formulated, which gives actually sometimes better agreement with the experiment. But we always restrict our discussion within the van der Waals equation of state, because it is easy to use first of all, and it is very elegant model in the sense that conceptually it just depends on the thinking that the main 2 assumptions that actually gave rise to the ideal gas law. One is the gases are behaving as a point mass, they do not have any volume. So, that is wrong, and the second thing is that the gas molecules do not have an intermolecular attraction, that is also wrong. So, once you actually invoke this idea that the gas molecules have a finite volume as well as there is an intermolecular interaction, then actually you can very easily by introducing some empirical constants A and B, you can actually arrive at the van der Waals equation. So, let us summarize what we have discussed under this topic. So, we first started with the properties of gases, and we talked about first the ideal gas law, and there we talked about what are basically the various what are the basically concepts of the equation of state, and then we talked about the various parameters like we talked about Maxwell-Boltzmann distribution, and under the Maxwell-Boltzmann distribution we talked about what are the expressions for various velocities that you can think about, like RMS velocity or the average velocity or the most probable velocities. What we did not discuss is that that velocity distribution you can easily also convert to speed distribution, in the sense that you can always ask this question, that what is the fraction of molecules that have energy in the range E to E plus D, and that is very easy to understand, because all you have to use is this relation, the average kinetic energy is nothing but half m v square, and then from that you can actually plug in whatever you have to write v in terms of epsilon and also dv in terms of d epsilon, and then actually you can write the distribution function in energy. So, it will be f epsilon d epsilon, okay, and you will have some functional form where actually you will see that it will have some constant times epsilon to the power half e to the power minus epsilon by kBt d epsilon, and you will have a similar curve like the Maxwell-Boltzmann distribution if I plot f of epsilon versus epsilon. So, this is a notation like this epsilon notation for energy. Sometimes you write it like this, sometimes you write it like this. So, it is just a notational thing, and then we found the expression for, after calculating the various expression for various speeds, we actually, or the velocities, we talked about the real gases, and where we talked about first the deviation of the real gases from the ideal behavior, and then we talked about a particular law or equation of state, which is the van der Waals equation of state, which is P plus n square A by V square into V minus NB is equal to RT. Now, again this is a model, and reality is something like which is always cannot be truly explained by any model. So, there will be always some deficiencies in every model. Now, you refine your older model to get a better model, and so that actually it can explain the reality of the experimental observations much more in a much more better way. But always you have to keep in mind that this is just a model. And one particular thing that we did not discuss here is that if we increase the temperature, how the Maxwell-Boltzmann distribution actually look like. So, we plotted it for a particular temperature. If we had increased the temperature, so the curves actually gets more and more flattened. But always keep in mind that the area under the curve will be always equal to 1, because this is a probability distribution. So, as you can see, the most probable speed actually shifts towards right, which is obvious, because if I increase the temperature, we will have more and more speed of the gas molecules, or the average speed or the most probable speed, everything will increase, because everything, as you can see, is proportional to square root of temperature. Each of these velocities, like the average velocity or the most probable velocity or the root mean square velocity. So, actually if I increase the temperature, the curves will actually shift towards right, and they actually flattens out more. And similar observation is also seen for the energy curves, because energy is nothing but proportional to the square of velocities, and then since v square is proportional to absolute temperature, so energy is proportional to the absolute temperature, which makes sense, because kBt is, or RT is a unit of energy. So, the curves will get similarly flattened out for different temperatures. So, this is plotted for T1, T2 and T3, where basically T3 is higher than T2 is higher than T1. So, stop our discussion on the properties of gases right now, and then we will first give you an overview on the laws of thermodynamics, where we will again will give you a very brief overview, but we will give you sufficient amount of homework, as well as we will give you some handouts which will actually summarize all the things which we are covering in the lecture, so that you can first have a look at the summary of the lecture notes, and looking at the equations, and also the formulas, and some worked out problems also will provide. And then after having after actually watching the videos and going through all this the notes or the handouts, then you can actually attempt the problems which will be given to you, and then after a certain time the solutions will be released, which you can always look at and check your answers with that. So, this is the overall plan of this course, and I hope you have already started enjoying it. Thank you.